US Physics Olympiad, year 2020, USAPHO, final round. Problem A2. Swoosh. In 1851, Leon Foucault built a pendulum 67 meters tall with a 28 kilogram weight. He connected it to the top of the Pantheon in Paris with a bearing that enabled it to freely change its plane of oscillation. Because of the Earth's rotation, the plane of oscillation smoothly moved over time. If we imagine a large horizontal clock under the pendulum, if initially the oscillation went from 12 to 6, later on they would move to the 3-9 plane, for example, as shown in the figure below. Perhaps surprisingly, the time it took the oscillation to go back to the original plane is longer than 12 hours. In this problem we will investigate why this is the case and what the shape the pendulum traces out. Figure 1. Left. A schematic of Foucault's pendulum. Right. The pendulum motion projected on a horizontal plane in the rotating lap frame. First, consider the case of a Foucault pendulum installed precisely at the North Pole with the length L. We denote square root from G over L equal omega. The angular velocity of the Earth is capital Omega. John is an observer looking at the pendulum from a fixed point in space. At t equals 0, he sees the pendulum at position A0 and with the velocity 0v in the xy horizontal plane. Question A. For John, what are the approximate equations that describe the motion of the pendulum in the xy plane? You may assume that the amplitude of the oscillations is small. We define the coordinates of the pendulum at rest as 0, 0. Question B. What will the coordinates x, y in John's frame be at a later time t? Question C. Ella, an observer, resides at the North Pole, is also looking at the pendulum. What are the coordinates x tilde and y tilde as observed by Ella? Assume that at time t equals 0, the coordinate system of John's and Ella's overlap. Question D. What is the speed of the pendulum bob observed by Ella at t equals 0? Question E. Find the initial coordinates for A, V such that as measured in Ella's frame. Case 1. The pendulum passes precisely through its resting position. Case 2. It has a spike at the points of maximal amplitude, see figure below, instead of a rounded trajectory. Figure 2. Two possible trajectories with a spike, left, and more rounded, right. In a rotating frame, a fictitious force known as the Coriolis force acts on the particles. For Foucault's pendulum, the Coriolis force acts primarily in the horizontal plane in a direction perpendicular to the velocity of the mass in the Earth's frame with magnitude F equal 2m big omega v sine theta, where m and v are the pendulum's mass and its velocity, and the theta the latitude, 90 degrees for the North Pole. Note that when the velocity changes sign, so does the Coriolis force. Question F. How long would it take for the plane of oscillation of Foucault's pendulum to return to its initial value in Paris, which has a latitude of about 49 degrees? Solution for problem A2. Question A. For John, what are the approximate equations describing the motion of the pendulum in the xy plane? You may assume that the amplitude of the oscillations is small. We define the coordinates of the pendulum at rest as 0, 0. Solution. Because John's reference frame is inertial and the point of attachment is stationary, this is a free-moving pendulum obeying simple harmonic motion in each axis. It means that our equations are ax plus omega square x equals 0 and ay plus omega square y equals 0. That was answer for question A. Question B. What will the coordinates x and y in John's frame be at a later time t? Solution. Because coordinate system of John is inertial frame of reference, in common case, solution for the system which is in question A will be r equal a cosine omega t and v equal negative a omega sine omega t. If we use initial position and velocity like this, in that case solution will be x equal a cosine omega t and y equal v over omega sine omega t. So that's the solution, and this is the answer for question B. Question C. Ella, an observer, resides at the North Pole, is also looking at the pendulum. What are the coordinates x tilde and y tilde as observed by Ella? Assume that at time t equals 0, the coordinate system of John's and Ella's overlap. Solution for question C. In previous question we found that coordinates in our inertial frame of reference we had x equal a cosine omega t and y equal v over omega sine omega t. In the frame of reference which rotated by angle big omega t, we had coordinate transverse in rotated frame of reference. If we put x and y in frame of reference L, we have x tilde equal this expression and y tilde this expression. This is the answer for question C, and that was solution for this question. Question D. What is the speed of the pendulum bob observed by L at time t equal 0? Solution. In previous question C, we found that coordinates x tilde and y tilde in L's frame of reference are like this. So to find what are equations for velocities, we have to take first derivative by time from these formulas. After that put time t equals 0 to these formulas. So finally we have vx tilde equals 0 and vy tilde equal v minus big omega multiplied by a. So that's the solution and answer for question D. Question E. Find the initial conditions for AV such that as measured in L's frame, the pendulum passes precisely through its resting position. Solution for question 1. If we take equations for L's coordinates, we have these two equations. So first we need to take a first derivative from both of them and look what are conditions for simultaneous Vx and Vy equal 0. That happens only if V equal 0. In other cases it's not possible. So that's a solution for part 1. Question 2. It has a spike at the points of maximal amplitude. See the figure below, instead of rounded trajectory. Solution. To have a spike, we need the velocity to vanish at the extremal points in LS frame. This gives the condition V equal big omega A. Note that in the LS frame, this implies releasing the pendulum from rest at some amplitude. So that's the answer for question E, part 2. In a rotating frame, a frictious force, known as the Coriolis force, acts on the particles. For Foucault's pendulum, the Coriolis force acts primarily in the horizontal plane, in a direction perpendicular to the velocity of the mass in the Earth's frame, with a magnitude F equal 2m big omega V multiplied by sine theta, where m and v are the pendulum's mass and its velocity, and theta the latitude, 90 degrees for the North Pole. Note that when the velocity changes sign, so does the Coriolis force. Question F. How long would it take for the plane of oscillation of Foucault's pendulum to return to its initial value in Paris, which has a latitude of about 49 degrees? Solution. Since the expression for the Coriolis force only depends on the combination omega sine theta, and since the solution at the North Pole must be pi over omega equal 12 hours, the time at the general latitude must be omega sine theta. And for Paris we have pi over omega sine 40 degrees, which is about 16 hours. That was a solution for question F, and that was a solution for all problem A2.